Hello everyone, this is my fifth video on electromagnetic theory, and in this video we are going to discuss when the curl of an electric field will be zero and when it will be non-zero. First, let us try to understand what we mean by curl of a vector. And to understand this, let us take two examples of wave pattern on water surface. In the first example, the water waves are radially coming out from a particular point. The second example, it is a circulating water waves. Now let us draw the velocity vector distribution for both the cases. For the first example, the velocity distribution will look something like this. And for the second example, the velocity distribution will look something like this. Now let us place a mini paddle in both these cases. Now, which one is going to rotate? Obviously, the second one is going to rotate. So, the curl of a vector is related to the circulation behavior of the distribution of the vector. Now, without doing any mathematics, we can say that the curl of the velocity vector for the first case will be 0, and the curl of the velocity vector for the second case, it will be non-zero. Now, let us come back to curl of electric field. First, we'll consider the case for electrostatics, that is, the charges are at rest. If I place a positive point charge at origin, then the electric field pattern would look like this. If I replace it with a negative charge, then the electric field pattern will look like this. Now, let us imagine a hypothetical mini paddle, and I'm placing it at the origin. Now, if this mini paddle starts circulating, that means the curl of E will be non-zero. But by seeing the field pattern, we can easily say that this mini paddle will not circulate. So the curl of electric field vector will be 0. Similarly, let us place the same mini paddle in the second case. Here also, the paddle will not rotate. So the curl of electric field will be 0. Now, let us consider the case of an electric dipole, which is a system consisting of two equal and opposite charges. The electric field pattern of an electric dipole will look like this. Here, the electric field will originate from positive charge and it will terminate at negative charge. Now, if I place the hypothetical paddle in the center, then based on the field pattern, we can easily say that this paddle will not circulate. So, the curl of an electric field for this case will be 0. Now, the next question is, when will be the curl of an electric field be non-zero? Or in a very simple language, we can ask, when do the electric field vectors circulate? To understand this, let us take an example where the magnetic field is a function of time and it is along the z direction. Please note here that the magnetic field depends only on time, not on the xyz coordinate. Now, if I take a 3D space, the magnetic field will be pointing along z direction and it is changing with time, and we can represent the magnetic field vector like this. Then the corresponding electric field vector will look like this. Now, based on the field pattern of the electric field, we can say that for this case, the curl of electric field will be non-zero. From the previous example, we have a very interesting question here. That is, why the electric field is circulating. To understand this, let us visit the Faraday's law. Faraday's law says that the line integral of the electric field is equal to the negative of the derivative of magnetic flux. We can write this expression as curl of E is equal to minus of the derivative of magnetic field. Now, in the previous example, the magnetic field was varying with time. So, using the second formula, we can say the derivative of magnetic field will be non-zero and the curl will be non-zero. But right now, let us try to understand why E is circulating. Let's take the magnetic field, which is a function of time, and let us take a circular part. And in the circular part, we have a dl vector. Let us now try to evaluate the integration. So using the right-hand thumb rule, we can say that electric field will be always parallel to the dl vector. And also, the point on the circular path is at equal distance from the vector. So using these two concepts, we can take the E outside the integration. Now if I evaluate this, I'll get E into 2 pi r. We'll call this as equation 1. What about the magnetic flux? It will be given by the area into the magnetic field. Now if I take the derivative, then we will get this expression. We'll call it as equation 2. Now using equation 1 and 2, we can finally write down the magnitude of the electric field, which is given by this expression. Now what about the direction of the electric field? So in the beginning I told E is parallel to dl vector, and dl vector is always tangential to the circular path. Now using this concept, we can say the E direction will be along the phi cap direction. Now using these two information, we can finally write down the expression of the electric field, which will be a function of r and t, and the expression will be given by this. Now the phi cap direction will be always tangential to any point on the circular path. That's why the electric field is circulating. At the same time, in the previous example, I have shown the electric field vectors to be on a concentric circle. That is because in the last formula, we can see that if the point which we are trying to evaluate, if it is at equal distance from the origin, then r will be constant and the electric field will be same throughout the circle. There is an alternative viewpoint on curl of electric field. If the curl of electric field is 0, then we can write the electric field as the negative of the gradient of scalar function. If we can write this expression, then the electric field is said to be conservative. And if the system is conservative, then the line integral is independent of path. But if the curl of E is non-zero, then the system is non-conservative. And if the curl of E is non-zero due to time-varying magnetic field, then the expression of electric field, that is negative of gradient of scalar function, is not valid. And we have an alternative expression, and the extra term, that is a negative of the derivative of vector potential, this takes into account of the electric field generated due to the changing magnetic field. Thank you everyone for watching.